All right, welcome back. We are COMP2142. That's Game Artificial Intelligence 1 in the winter 2026 semester at Georgian, and it's week 6, part 1 of our broadcast and recording together. In this part, we're going to be talking about data structures. Again, last week we talked about sorting algorithms. This was done asynchronously. And we kind of worked on the second part of obstacle avoidance. And this week we'll talk about searching algorithms. You can't really do searching without sorting. First you got to sort everything in order and then you can search it. That's typically how we do it. And then we'll be finishing off our assignment 1 in terms of all the requirements you have for assignment 1B. Same time, we're also going to be doing a bit of an exam review. And just again, for those people who are not part of other courses but are only part of this course, next week the exam will be done remote. It'll be kind of delivered Sunday or Monday time frame. And you'll have the document, you'll have the week to get it done, and it's an individual assignment. That's what's happening next week. Let's talk a bit about it. Similar to what we talked about yesterday. It'll be remote about 2 hours approximately in terms of the complexity. We will work using our current steering behavior project. So the one that I build up with you as of today will be the one that you'll use for your project, and I may add a couple of additional things. Okay, so that's something I'm going to be doing. Some possible tasks, some other steering behavior, a wander, pursuit. Could be that I want you to, kind of develop something new, right, related to steering behaviors. Okay, if I do get you to do something like a new steering behavior, I'll give you the pseudocode. I'll provide it for you, and then you create the steering behavior from there. You may modify your HUD to include additional tools, whatever those are going to be. So that's kind of stuff that you may be doing next week. All right, other things we're going to be talking about today is searching algorithms, recursion, and hashing. We will do a bit of an exercise, a challenge, again, for you guys to see if you can do it. So what I normally provide, like I did last week, is I provide the C++ code, and then I say, okay, so like, can you do the blueprints from the C++ code? And it'll give you practice doing that kind of stuff and converting some piece of pseudocode or C++ code into something that you can use from an algorithm perspective. So that's something that we're going to be working on today. So let's talk about search algorithms. And just a review, we talked about sorting algorithms last week. And we also talked about collections, different kinds of collections. Linear collections, kind of nonlinear collections, different kinds of things where in terms of groups, different kind of groupings like sets and maps and that kind of stuff. So non-indexed, and that kind of thing. So we're going to be continuing with that, and we're looking for a given value in a list or some kind of array. This might be the problem that we're trying to solve with this one. And there are two ways of doing it, two fundamental ways. One of them is some kind of sequential search used when lists are in some kind of random order, so that's when they're not sorted, and then a binary search when used in a list that is completely sorted. Typically we want to sort the list first. It's a lot easier, and it kind of decreases the complexity of the search algorithm. Okay, but sometimes we don't have an option, especially if we don't have access to manipulate the list. We can only if we can only work with data, but we can't modify any data. We have both options. So let's talk about sequential searching. So again, this is the first type, and really what it is, it's also called a linear search. It's really simple to implement, but what we do is we start at the beginning of the array or the list and compare each accessed element that you're searching for. If you find a match, the search is over. If you get to the end of the array without generating a match, which is also possible, maybe the value doesn't exist, then you kind of respond or return something that tells you it doesn't exist. That's the sequential searching part. So here's an example of the sequential search algorithm. Again, I've written this so you can implement this in C++ with Unreal Engine. So you can see that it's a T array. So T array is your standard collection that you'd have in C++ for Unreal Engine. I mean, clearly there are other kinds of collections that you'd have in C++, but we use the one that's built in a lot of times in Unreal Engine because it's managed. You don't have to worry about memory, right? So all the kind of stuff that you would normally have to worry about with raw arrays or even linked lists, if you're going to use a linked list in C++, T arrays take care of that all for you, which is pretty cool. So first we save the size of the array. So array num saves the size, and then from there, and we talked about this last week, again, you may have not caught this, but we don't want to use array num here, okay, inside of a for loop. I talked about that last week. If we're thinking about optimization and we're looking at big O notation, so the complexity of, for example, of an algorithm, to reduce the complexity and improve performance, we don't, kind of when we're actually doing the for loop itself, we don't do it here, where we kind of calculate the length, because getting the length of an object is a function that we're calling. We're saying calculate the length. So we do it one time, and then in that one time, what we do is we save that value, and then we access it in the for loop. Otherwise, every single time you loop, you're accessing that value. You're calling that function. And that's what I talked about last week. So again, if the array index is found, then we found the value. Otherwise, it's false. It's very simple to do a sequential search like this. Sometimes what we're looking for is a minimum or a maximum value in a list. And again, in an ordered array, that's no problem because we can look at the beginning or the end of the array. That's really trivial. But in a unordered array, it's more challenging because then we have to look for, we have to kind of loop through and kind of have a variable that we keep track of. And then that variable is the thing that's going to be the thing that we're comparing. So here's an example of find min. And let's suppose that the algorithm is not sorted. We don't want to suppose that it is. So again, if my array number, so my length of the array, that's what this is, the array length is 0, then we do an early return. Okay, because I mean, clearly there's no, we didn't find the minimum, right? If, on the other hand, it's not true, we get through this one, then minimum is the first element of the array. That's what we do. And then we loop through each element of the array, right? Now then again, you can see that we did array num here, but we would probably put it outside here. And then if array is less than min, then min is equal to the array, and that's pretty simple. It's again a sequential search through the array. So a sequential search, not the most efficient search. Here's the max. Max and min are identical. The only thing is that we're comparing minimum or maximum, and then we're saving those values. So again, the fastest search we can do when we're looking at performance, when we're doing a search, is if the thing that we're searching for is at the first element in the array. If that's true in a sequential search, we're done. We're good to go. And the worst case scenario is it's right at the end, the last element that we're searching for. So that's the worst case that we can kind of devise as well. So so one thing that we want to do is we can kind of make it so that the thing that we're looking for is at the beginning of the array. And this is something called a self-organized array. And so the way it works is we can modify the sequential search so we can start looking for that value. And the swap function that we talked about last week, which is very standard. Take a look at that swap function again. We hold the value item, we hold the value in here, and then what we do is switch with item 2 and then swap back. This swapping mechanism is something you guys should know how to do. Like if you're ever going to go to an interview and they say like, how do I swap two values, as an example, what do I do? It's the simplest thing you can do, but you need to know it. Okay, it's something that should be part of your programming vocabulary, if you will, right? So we tried to implement that. I'm just going to bring up this again. So in my blueprints, we had that, but we also had data structures, and we had sorting algorithms. This was a thing that we did last week with bubble sort. Okay, I also talked about last week, just as a review, that you can break a lot of these things down, you know, kind of break node links, but you can also expand the node. And it's only available for some nodes. These gray nodes, as an example, a lot of times give us the ability for us to break the node. And notice that there is a little M next to it. Okay, so if I actually click on the little bubble, there's this little M here. M means macro. So really, if you think about what a for loop is in blueprints, it's a macro, right? And a macro is similar to a function, but it's not a function. It's something that we write inline. So here's another one. You can see that both of these are gray, not green or purple or whatever. They're gray. And anything gray like that, a lot of times we can just go and expand node. So we did it last week by expanding the for loop and trying it that way. But this is an example of what we did. And here's the swap, this swapping algorithm, you know, that we used, where we swapped, you know, kind of one thing for another thing. Okay, so this is the idea of the swap. Today we're going to do another one, and I'm going to make a new function library. Let's try this together. Again, I want you guys to practice. So, so if I go to Blueprint, and notice that there's other ones too. There's macro libraries here as well. You can use those ones, but we're going to make it a function library. So we're going to call this BPFL, so Blueprint Function Library, and this is searching algorithms. Okay, again, I'm basing this off of the last thing that we did, but I have a folder called data structures. Some maybe you didn't follow along last week, or you know, you just didn't watch the video. There's lots of things happen for people, but let's just do the searching algorithms. So again, whenever we create a, I'm just going to go and make sure that the editor preferences are correct. Whenever we search for or we create a blueprint function library, then what we want to do is we need to have at least one function in that blueprint function library, which is what we're going to add in now, right? To show you how this works. Okay, so what we talked about last week is you know, there's certain things that won't work properly, you know, as an example, because they require a world context, right? So be careful if you're asking for the function to do something that you need the world context for, okay? So again, we're going to come back to this, but you need at least one function, and right now it's called new function, but we're going to change this to whatever we're going to do. Let's go back to this one. So if I want to do this self-organizing search, and if I want to do it, let's take a look. It's a sequential search, but it's a self-organizing sequential search, which means it tries to swap out the value that you're looking for at the beginning of you know, kind of the array that you're getting in. So it takes in an array, a T array of integers in this case, right? And it also takes in an S value. The S value would be the searching value, thing that you're searching for. Okay, so let's try and program this together as an exercise. Please follow me. This is going to help you with maybe your exam, maybe it'll help you in other things, but it's you know, you need to know how to do a few algorithms here. So help me out and do it with me. Okay, like as a bit of a challenge. We're not going to implement the entire thing. I also want to implement this swap and see if we can make it work again the way it is. So first is sequential search is what it's called. So I'm just going to take that same name, go back here and kind of put it in. We'll call it sequential just to make it the whole thing. Here's my sequential search. The sequential search will take in an array. So again, if I go to input and if I input an array, so this is an integer array. Integer array. We're just going to call it integer array. And it's going to be of type integer, and it's going to be an array type. Okay, so some integer array that you're getting in, that's a sequential search. And then what we're also going to take in is a search value. So let's do that. So search value, and this will just be a simple integer, the thing that you're searching for. Okay, so it's single. We can also put in an int array or whatever, but integer array is fine. So those are the two inputs. The next thing is we want to get the size value. You want to save that size value. So again, inside here, we want to have a local variable called size. And size would be an integer. Here's that integer. And then what we want to do is we want to save the array number or count. So if I do something like get integer array, here it is, and I want to get the count. So get. So if I go count or size, it'll take me to length. I talked about this last time. And I want to save this. So I don't want to keep, this is a computation. This is something that doesn't happen automatically. You have to actually call, this is a function that we're calling here. I don't want to call this function every single time I'm looping. That doesn't make any sense. So instead of this, I want to save it in size. So I want to save it here. That's the first thing we're going to do. So save the size here so we can use it again. That's what this is. Okay, and we're going to do this in a sequence. So I'm going to just put a sequence node. Here it is. And we're just going to do this, move this aside, and there we go. So that's the first thing we're doing. All right, so again, think about this just like you're programming. You know, you get a function, and then sequences are just a new line, another line, another line. You're doing this in order. That's what a sequence node would be like. Okay, and then the next thing is a for loop. So let's do a for loop where we're counting from 0 to index is less than index size. So, okay, so if I do that, that's the next thing I want to do. So let's do a for loop. Now we can do a for loop or a for each loop. I'm just going to do a for loop just to keep the, the exact thing as much as possible. There's my for loop. And then the first index and the last index. So the first index is 0 and the last index is size. Okay, so size is less than size. Okay, that's what we're saying. But what we have to consider is last index is not less than. It's the last index you want to go to. So you want to do size minus 1. We had that wrong last time. So here's size, and then minus 1. So size minus 1 is the last index, right? Because you want to go 1 less than size. And that's how a for loop works. It goes from 0 to, it's inclusive. These two things are inclusive, first index and last index, right? So that's how the first thing is. And then inside of my array, so this is inside the loop body, or inside the loop, I meant, you have an if, the first if statement, which is if my array index is equal to my search value. That's the first thing. So we're going to search for that. So here's my index, and then the array. So let's get the array, and then get. Again, we can. It doesn't matter if you get a reference or a copy. I'm going to get a reference in this case, though, and I'm looking for the index. This index here. So this is what I'm looking for. So if my array, if my array index, right, is equal to thing, so I want to say equal, which starts, kind of a conditional statement, is equal to the s value. So this is the search value. Here it is. If this is the case, right, and that's true, branch. So I'll put this down here, and we'll just do one of these for now. There we go. So if this is true, then we have another if statement. If my index is greater than, and if my index is greater than 0. Now we could code this together if this is true and, but if my index is greater than 0, so we'll say index. Now index, instead of me pulling this around, we can save this as the index integer, right? So I can kind of like say, let's promote this to a local variable. If I say index, by the way, it will work, because even though this says index, it's an output from this macro, right? So if I just do one of these, then I don't have to do one of these, right? Instead, I can just say index, like so. Makes it look nice. And we can also move it aside. I prefer always when we code with blueprints to kind of make it as clean as possible. So now that we have our index, we can say that if index is greater than 0, so greater than 0, that's the next conditional branch. So those are the two components there. That's the second if statement. So if we pass both if statements, if we fail our first if statement, we just return. Look at that. Like we, if we come here, we kind of loop. We go to the next index, the next index, the next index. That's what we're doing. And then now inside this one, we're going to do the swap. Okay, so this is where the swap happens, where I pass in an array item, so the item 1 and item 2, and then what it does, the swap, it actually swaps those items out. Now notice that there are, with this function, there's ampersands. Ampersands means we're passing in by reference. That means when we actually do the swap here, I don't need a return type in this function because it just swaps them by reference. So I'm kind of peeking inside of that memory location and the other one, and I'm like, okay, just swap them around. So we're going to do something like this again. We could also just do it in here, right? Actually do the swap in here, but let's make that other function like I said. So let's try this out again one more time. So I can add another function called swap. Here's my swap function. And the swap function, I'm going to take in two values, right? Item 1 and item 2. Now, one thing to note is when we put inputs in, here are the inputs. If I open this up, notice it says pass by reference. That's actually an option, pass by reference. Instead of passing by value, right, I can pass by reference. So this is a pass by reference. And then I can say this is item 1, right? And then we can kind of add another one, and this will be item 2, right? And again, what I can do is pass by reference. Both of those two things now are passed by reference, okay? So what if I didn't make one of those pass by reference? Notice that there is a different pin type. Take a look at that, right? So the pin looks different than pass by reference. Pass by reference is actually pretty cool. We don't want to make these const, but we could make them const as well. So there is quite a bit of control here when it comes to functions, right? So here's my swap. I want to do this, but I need a local temp variable. So I make a new variable called temp, right? And all I want to do is I want to set temp to item 1. So I said that set temp to item 1. So I can say this is what that is. So the first thing I do is I'm like temp is equal to item 1. And I can also do it the other way where I can say get item 1 and then do it this way. If you're more prone to doing it this way. So that's the first thing I want to do. I want to do a sequence node right here. Here's my sequence node. And then once I swap the first item, the second thing I'm going to do is swap the other one. Item 1 now is equal to item 2. So I'm going to say, so item 1. So that's, now, one thing to note is when we set a value here, item 1, we can do this in a regular function, but unfortunately we can't do it. Like if I said something like, well, I want to, you know, kind of set, if I go like this, set item 1, I can't do set item. Take a look at item 1. So if I can get item 1, but unfortunately I can't set item 1. So even though my function in real C++ allows me to do this, I can modify these things. We have to consider that these things are unmodifiable. It's almost like as if I have to create, you know, new variables in order for me to do that. And that defeats the purpose of my pass by reference. Does that make sense? Have I lost you guys? Hopefully not. But this is the first thing I want to do. I want to get this item and swap it out. So we really do need a return. Like we need to return out item 1 and item 2. Yeah, let me just do this again. So even though we're passing by reference, okay, we're passing in by reference, I can't modify any inputs that come into a function. I can't, not in blueprints. This is a disadvantage. Okay, I can't do that. Like, you know, as an example. And the reason for this is because if I do something like, well, I want to set item 1, set, and I do item 1, I can't. It's not possible. I can't set the item, right? So it's almost as if I take item 1 and I swap it and I return it, you know, that kind of stuff, like new item 1 or whatever, swapped item, you know. So that's kind of like how it's going to be, right? A and B, and then I'm kind of swapping B and A, you know, that kind of stuff. I can't do that. And also the other thing is, if I add a return node, I got to talk about functions here. I can't have the same names on the way out. Like if I go here, if I go item 1, Notice it doesn't allow me to do that. I can't return the same items out that I put in, right? So this is kind of what we had a problem with last time. So let's try this out. So here's these two things. I need two parameters on the outweight, right? Because even though I'm kind of putting this on the inside, then we're swapping it out on the out when I come out. So that's why last week when I was talking about it, the nice thing would do is to do something like this, where we just swap the items like this. It's literally just like whatever incoming, we just swap on outgoing. But again, that kind of defeats the purpose of this whole function. This is why sometimes things work okay in C++, but they don't work okay in blueprints. I was trying to tell you this, guys, last time. I'm not sure if you guys saw it or you watched it, and I want to mention it again. Right? Sometimes you can't. It's not a one-for-one. It's not a one-for-one. Okay, so that's why, like I say, the swap function is useless for us. We can't use it. So we're going to do the swap inline right here instead. So the way to do that would be this, where I want to swap array with, we need a temporary value here. Let's do that. So here's temp, right? And then what we want in here is we want to set temp. Here's where we set temp. We'll do a sequence node. Here's my sequence node. And then I want to set my first value. I want to swap with my second value. So this is array index and array index -1. We're going to swap those two values. So we're going to say that the first thing we're going to do is temp is equal to array index, the first one. So that's going to be array index. So get array. Here's my array. And I want to get this one. Actually, this whole thing. And I'm going to say that I'm going to save, I'm going to save my value. I'm going to save my, my array index, the value that's sitting inside of array index. I'm going to save it inside of the temp value. That's what I'm doing. That's the first thing I'm going to do, right? And then I want to make it so that my array itself, I want to set the array. Let's do that. So here's the setter. So I'm going to say integer array, and then I want to set array element. So there's the setting. I want to set array element, my index, like it says here, -1, index -1. So index -1. That's still okay. Here's my swap. And the thing I'm going to swap in there, right? So I'm going to set my array index to index -1. That's the one it's going to be. So sorry, this is the other way around. This is actually looking at index -1, and I'm going to set my array index, this one, to index -1. So whatever the value is, the item is index -1. Actually, I mean that's not correct. It needs to be the new item that I'm getting. So I'm actually going to get index -1. So array let's do that again. I want to get these two things and put that in there. So I need to get the item from the array at index -1 and save that in the area where the index is currently, the previous item is in. So this is the swap, the first part. And then, once we've done this, we want to do it again, but the other way around. So I want to do the array set element. We've stored the previous value of index, whatever the index was, inside of temp, and now we're going to get that value from temp and store it back in here, right? For item 2, right? So that's array -1, and that's the swap. Okay, and that's how it works. This part right here is actually the swap. The swap. Okay, is that clear? Clear as mud?
Question.
Yes.
What does the swap by reference node do, Ben?
Swap by reference, if you do that.
It's not swap. I mean set
Oh.
by reference. Sorry.
So you're saying array index integer? This one?
Like when the nodes like in the thing is set by reference.
This one.
Value.
Yeah.
Yeah.
So so instead of, so here's my array, right? Set array of integers. All right, and there's the value, another array of integers that you pass in here, and it sets this array to the other one. It points it to another array. That's what it does. Because notice how they're both arrays, right? So it's almost like I want to make this one equal to another one, like actually point to another one in memory. Sometimes it's important for us to do that because we want to rename it to something else. Let's say, for example, inside of a function. So if I pass it in as a function, I want to be able to modify it. But that's not what it would be. It's this, what we want to do. So does this make sense? Is anyone confused by this? Now, what if, here's the next one. What if I took this, like I said last time, this part right here, and I turned it into a function. So I can collapse it to a function. So if I collapse to a function and I call it swap, right? Well, the problem is if I go into that function, then I get all this. But notice that integers, all these things are grayed out because we don't have any of that stuff, right? We don't have any of these things, so it's completely useless. It wouldn't work, right? I'm pointing this out because people get these fancy ideas about how this would work, but it can't. It just, it doesn't have the ability to do it. Not everything is a one-to-one, is all I'm saying. Not 100%. Most things are. And so this, although it looks, pretty long and complicated, this is it. This is this function right here. This is this little sequential search. Okay, so sequential search, the way it would work is if we give it an array and some kind of search value, it will return Boolean. It'll return bool when the array is found. So now let's fix it. Let's finish it. So if index is greater than 1, we swap and then we return true. So that's inside of the if statement, the inner if statement here, right? So the first thing we do is do this, right? We do the swap. That's in the inner if statement. We do the swap. But on the outer if statement, which is this one, right, we can do, if this passes, if this is true, if array index is equal to the search value, then what we want to do is we want to return true. So that because we found it, as an example. So we can do a sequence node. And then inside that sequence node here, so the first part of the sequence node, if you think about it, is the if statement, and the second part is the return. So this one is add return node, and we just want to return true. So we're going to have an output that is a Boolean type. Here's the Boolean type, and the Boolean type is going to be item found, right, kind of thing. So if I found it or not, that's what I'm going to return. I found it, kind of thing. It does exist. That's all I'm checking to see it does exist. It's not returning where it exists. I'm not telling you, like, this function doesn't tell you where you found the item. It just says I found it. Now the thing is, because we're doing a self-organizing sequential search, if I find the item, then I take a look at my array index that I found the item, and then I swap it. You know, that's what I'm doing it. So I swap it out with the item that I found. Array index, whatever the index would be, I swap it with this one. And then I return true. Okay? Otherwise, as an example, if I've gone through this for loop over and over again, you know, as an example, then we were going to return false. So that's the other thing that's going to happen. So if it's false, if we branch through the entire thing, so we go through the for loop, which is this one, and on completed, if somehow we're able to make it to the completed part, you know, because we've branched, here's our branch, this is the first thing we're checking, right? So this is, we're setting the thing, and then we're checking to see if this condition is true, and then afterwards, what happens? Well, we break out of the for loop when it's, if we're able to complete the for loop, then we want to return false, which means before the for loop in here, if we ever get to this part, we want to have another, you know, kind of node here. So add return node, and here we'll be returning false. So item found here is true because we did find the item, but item found over here is false. And this is what we've done. We've created the same sequential search algorithm. Questions around this? Anybody? So you may get a piece of pseudocode, is like what I'm saying, right? And it may not be now, but I may give it to you, you know, and say, do this. Like, you know, replicate this thing. Like, you know, convert it from C++ into a blueprint. How do I do that? And it has to be pretty clear, pretty close to what I'm looking for. Now, there's some optimizations we can make here, right? If you really want to. And you might be able to see an optimization. Like, for example, maybe instead of a for loop, you might want to try a for each loop. That might change the way this works or whatever. But I recommend as much as possible to make this as clean as possible. So let's try this out really quickly to test to see if this is good. So if I go to blueprints, and if I go into my grid character, where I did the last kind of example, I'm going to put it right in here. So after I've done all my initialization, this will be where I do my stuff. I already have an integer array for testing from last week. All I've done is I made an integer array and I've added a bunch of values. Here's some search values, right, as an example. And now I want to use that sequential search. So if I type in sequential search, because I've made it into a function library, it says target is BPFL searching algorithms. This is my function library. So I can access it from anywhere, any one of my blueprints, as long as I access it. Now it's available here, right? And all I want to do is if it's found. So if I want to find an item, right? So let's get my integer array. Here's my integer array in, right? And then the value that I'm searching for, let's say I'm searching for, let's make it fail first. So let's search for 14, all right? Okay, and what we're going to do is, what this does, I'm just going to pull this down a little bit to give myself some room. What this does is it returns a true or false. Now, if it only does return a true or false and doesn't modify anything, this is a great candidate for a pure function. So going back to my search, this one, my sequential search, I can mark it as pure, right? Compile and save. And if I do that now, it becomes this green node where all I care about with this is, did I find the item or not, right? And this can be very valuable. If it's found, then I want to do something. If it's not found, then I want to do something else. So I can kind of do something like a branch, right? This kind of goes along with the branch. And I'm looking for 14. And what we're going to do is, we can say if it's true, we're going to print string item found. And then if it's not true, we're going to print out very simply item not found. And let's print out different colors. So one is going to be a red color, and the other one is going to be a green color, and we'll say the duration is 30, right? This will be a green color, so we know this is the right thing. And we can even say the key to be different. So I can say found, not found. So they'll even appear in different places. Different keys. There we go. So now we have those two things, and that is our little test for our object. Let's compile and save and run. And what we should see is if it found it or not, okay, if we did everything correct. Now here's something that can happen. So notice like I've done this and my project crashed. So why did this happen? You know, as an example. This happens sometimes if I'm doing something that is going to go on forever. Like sometimes what it'll do is it'll tell me the reason why I said this is the second time we've crashed this week, which is awesome. If I can make Unreal Engine crash with blueprints, woohoo, right? So let's take a look at this and what it's telling me to do, right? So I'm just going to zoom down here, and we always go from this is the kind of the call stack that we're working with. So it says, let's see if we can get to that process event. We have a begin play, and this is where it happened. In my begin play, and then because that's where I'm calling it, right? And then I invoke a function at runtime, and it's calling a class. Doesn't really tell you much right here because it's calling script core, right? So it's not really telling you what the problem is right here. It just says it's crashed, right? Sometimes it happens, but it says assertion failed. That, you know, line 687. It's not really telling you anything really right now. It just tells you that if I look at the first line, it's some kind of script function. As an example, you know, I'm trying to get a return, and maybe I'm not getting a return value. Maybe there's not all values return. Maybe not all paths return a value. And if not all paths return a value, maybe then I'm getting a there's no it's not true or false, right? But that's weird. So let's go back and see what I can do to launch it again. Now, hopefully we didn't lose much, but if we did, you know, again, the exercise is really trying to understand, you know, how to use sorting and searching algorithms, right? So this is one where I'm actually, what I want to do is manipulate the, you know, the array. I want to manipulate the array, and I want to change it up a little bit. So let's see if we have that. Okay, so we didn't lose anything, which is good. Let me just go back to this and see what happens. So, so where we could have a problem is if the branching is false. So here in my for loop, my branch is false. It finishes, and I go to this item found is not true. You know, as an example, right? I pass in the integer array. Here's where it is. If I want to pass it in by reference, which is what it's passed in by default. Notice, so when I pass in the integer array, it's swapping the values out. That's what it's trying to do, right? If the value is not found, what happens if it's not found? So I loop through. Let's check this out and see if the value makes sense. And I'll do it here in the pseudocode. I'm looking for 14, you know, as an example, right? And so I'm saying I get the array size. So the size is, you know, how many elements I have in the array. And then if my array index is equal to my search value. So the first thing is 0 equal to my search value? So it would be no, right? And then if this is failing, it will just come to here. And then it'll go to the next one. It'll keep on searching sequentially until I find the value. Now, if it fails, it should just return false. That's what it should do, right? If it fails. If it passes, if I do find the value, then I do the swap. Now, we know if I look back at the grid character, and if I look at the integer array that I passed in, that 14 doesn't exist, right? Because I've checked to see if 14 doesn't exist, right? So that crashed everything. Let's do a file save all, and let's see if we can return a positive value. So it's actually, we're going to return true, right? So we know that integer array does contain 5, and it's the first element. So let's do that one. Nice and easy. So we're looking for 5. Is it true, right? Compile and save. And file save all, and then run. Hey, item found. That's what I was expecting, right? And let's try it again. Let's try it with 6. Let's see if we can go like halfway in. Is it going to still pass? So if I go here and I type in 6, and if I press play, Hey, item found, right? And what about if I press 3? Because 3 is here. Let's make this another value because we have 2 3s. We have a 3 here and a 3 here. Let's just change this value to 11. All right, so we're looking for 11, the last value in the array, right? So compile and save, and let's look for 11. Can we find the last value? All right, and if we found it, hey, we found it. So we can find values, no problem. But it's when we don't find a value that we crash out. That's what we did last time. So let's see if that's true again. I want to see if it crashes again. So I'm looking for 14 again. Actually, let's look for something else, some other weird number. Well, 14 was because of Valentine's Day, but didn't happen. Let's do 15. All right, so 15, and then if I compile and save, I'm looking for 15. Does it crash? No. Yay! It was okay. Maybe something else went wrong. Who the heck knows? Item not found. So that's what it should do. That's what it should do for us, right? So let's go back and put 14 in again. Maybe 14 is a cursed number. I don't know. Run it. Hey, it didn't find it. So you can see that it can find and not find items. Who knows what happened before? That's why I couldn't figure it out either. All right, so that works now. We know we have all paths do return a value, and we're good to go. Let's do one more test because I'm just curious to see what happens. If I do it here, does it run? So run it here. Hey, item not found. That's what I expected. Are you with me? So all this does is it returns true or false, sort of. Logan. So Logan, what's the issue? Talk to me, because I wanna talk it out with you guys. Which part don't you get, or are you stuck on, or it doesn't make any sense? Because my friends, I'm gonna give you something like this. It's gonna come, right? I'm gonna say do this, and then you're gonna be like, what does he mean?
I think it's just practice.
Okay.
The more I look at it, the more I'm gonna get it.
Let's do it again.
I was never good at array stuff personally. So.
I know. It's arrays are always challenging. Let's do another one. Let's do a whole other challenge. Okay, so we'll do the next one. So we've done this organizing search. That's what we've done now. Okay, so the sequential search, we've talked about it. It's very simple. It only swaps found items if they are located away from the beginning of the data set. That's what it does. So we swap a found item with the element that precedes it in the data set. And so what we do is every single time we search for an item, we keep on swapping it. So let me explain how this works. If I go back to this, so I'm looking for 7, then 7 is going to swap with 3. That's what's going to happen. 7 will swap with 3. Okay, let's see how this works. All right, so I'm looking for 7. Right? So if I go 7 here, and if I press compile and save, and if I test it, it says item found. But now we can go one step further, and we can look at the grid character, and I can look for that integer array because it's actually here, right? That I can look for. Right? Let's look at integer. So here's my integer array, and exactly what I said. 7 swapped with 1. So these two things swapped around, right? So 5, 3, 8, 7, 1. But notice that the original array was 5, 3, 8, 1, 7. So these two items, the last item swapped. So that's what this does. So why am I showing you this? Because that means every single time we search the array, it gets organized. It gets sorted more and more. It kind of pushes it the other way around, okay? Until the thing, if I'm searching for something more often, more frequently, then it's going to be at the head of the array, which means it's going to be faster. That's what a self-organizing thing does. The more you search for an object, if it's the very frequently searched object, it's going to be at the head of the array, which means it's going to be more performant than if it's at the back of the array, which is going to be terrible, right? Especially if it's like 10,000 elements in the array. Okay. All right, so that's what this does. Let's talk about another way of searching, which is a binary search. So now what we need to do is we need to have a sorted array first, and then we can find the thing that we're looking for. Okay. So how does it work? So what we want to do is we want to find an element inside of the array, let's say, that's sorted. So the first thing we need to do, if we're going to use this new array, I'm just going to kind of go over here like this, is I want to sort the array. Now we already have sorting algorithms in another data structure that's over here. We made that last week. So there's my sorting algorithms, and I have the bubble sort. That's what I used last week. Is a very bad performing sort, but it doesn't matter. Here's the swap again. Notice this swap is the exact same thing that we did last time, right? So there's a swap. We have an inner and an outer, whatever, but that's what it does, okay? So this is what we did last week. So if you don't have this, by the way, you can always go and take a look at my code from last week, but we need to have some kind of sorting algorithm first, all right? So we want to pass in the unsorted array, right? And then we pass out, we return a sorted array. So this actually has a return. So if I go to the bubble sort, in comes unsorted, out goes sorted. That's what happens. Okay, so we sort the array. Now, realistically, because we're passing in an array by reference, we don't have to have a return if I don't need to. So let me explain. So if I go back to my grid character, and if I take in my integer array, so get integer array, and I use, the bubble sort, here's my bubble sort, I don't have to pass this out. Because if I just sort my array, now notice my array is 5, 3, 8, 1, 7, like this. When I call the bubble sort function, what it's going to do is it's going to sort it in order, like in ascending order. Okay, so compile and save. And if I was to run this thing, then you can't see anything, but if I go back to the grid character, let's search for that, grid character, here it is, and my grid character, now notice that there are 2 1s, 1, 1, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 13. Okay, so let's say we have 2 1s and 2 5s. Let's see if that's true. So if I go back to the original array, then I have 2 1s, there's a 1, there's another 1, 2 5s, right? And it sorted it for us. So that's the first thing to note. Okay, it's not, it didn't make it unique values. It doesn't recreate the array, but I don't have to actually output anything, right? Because I'm passing an array, and when I pass an array into an object, I'm passing it by reference, it actually does the sort for me, right? That's what it does. So, so that's what it does. Okay, so if I want to, I can make a copy of that array on the way out again, but I don't need to, actually have an output at all. So that's what the sorting algorithm does. So sorting algorithm, it's already sorted. We're good to go. And so that's the first part. So now that we know the sorting algorithm worked, now we're going to make a new searching algorithm, which is going to be the binary search. Okay, let's take a look at how this works. So the way it works is, imagine you're trying to guess a number. It's the guessing game between 1 and 100, right? And the way we would do it is, remember how we would play this game? It's an old game that maybe some people have played before, like maybe around a campfire. I got a number in my head, guess my number. And then you have 5 guesses to get it right, as an example. All right, so here, it's a number between 1 and 100, and I have a number in my head. Someone try it out. Okay? Can anyone help me out? A number in my head between 1 and 100. Guess it. Tell me what the number is. Okay, so I go, oh, okay. All right, none of you guessed it, but let me just, Griffin, you're the closest. So let's just use Griffin's number, right? And I'm going to say, Griffin, it's too high. So now, Griffin, you're playing with me, right? Because you're the closest person. What's your next guess? It was too high. Hey, you got it. There we go. So that's how we would play the game. We would play this game where we would say, here's a number, guess high or low or whatever. So what this does is it's kind of the same thing. I'm looking for a number in my data set, right, as an example. And what it's going to do, the best way to break this out is to go to the midpoint. So if I go back to this, if I'm searching for, as an example, if I'm searching for 7, I'm going to start here. I'm going to guess the midpoint, whatever this midpoint is. The midpoint of the array, not necessarily I'm not guessing 5. Like the array could be arranged in different ways, right? As an example, So if I'm looking for 5, right, as an example, and that's okay, then I would find it right away, right? Because I'm going to go right to the middle point of my entire array. Notice that there are 1, 2, 3, 4 elements before the middle, and 1, 2, 3, 4 elements to the right of the middle. right? So to the left and to the right. So I'm splitting right in the middle. I'm kind of choosing that middle element, rounded down or rounded up. It's up to you how you want to code this thing, right? Then, if it's not that one, right? You know, as an example, we've now split the array into two parts, higher and lower, right? As an example, and once we do that again, and let's say we might try middle first, we might try the middle over here. So between 1 and 5, it's 3, you know, as an example. So is it this one, you know, as an example? And we keep on splitting it and splitting it and splitting it until we find the thing. This is actually, the binary search is actually very efficient, right? Especially if you're finding a value that's sorted. We know, you know, if it's higher or lower in a sorted array. Example, I'm looking for 7. I pass that value in. I go to the middle, it's 5. Now I know it's higher. So then what I do is I take this area, this group of numbers between 5 and 9, and then I split it in half. And I go here to 7. There it is. Right? And that's how the binary array works. It works instead of it passing, doing loops in a sequence. So worst case scenario, the worst performance for a sequential search is I got to search through each number. Worst case scenario, right? Because it's not here, it's at the end. Like the thing I'm searching for is at the back, you know, of the array, right? So that is possible. But the worst case is made better by the binary search because it splits it in half every single time. So it's at least twice as efficient if, as an example, you know, the number is not at the beginning of the array. If the number is at the beginning of the array, the thing I'm looking for, right, then this actually is worse. The binary search is worse because I'm not doing a sequential search. I'm looking in the middle every single time, right? Whatever number that is. So let's go back and look at what it looks like. This is the binary search. Okay, so now let's convert this. You know, this is the algorithm written in a C++ function. Let's convert this. There's no swapping to a you know, kind of a search algorithm. Again, it's on page 18 of your PowerPoint. Right? Let's convert this into, you know, a value. So here's something. The return, what this returns is an integer 32 or an integer, and it will return the index, right? So whatever the index is, it will return, right? Or -1 if it's not found. So this is a better function in some ways because the other one just says it's been found. I searched the entire thing and I found it. Okay, it doesn't tell you where it's found. If all you need to know is true, false, I found it, it exists or doesn't exist, the sequential search that we made earlier is perfect. It's fine, right? This one does not modify the original array. So nothing is modified here, all right? So we're passing it in as a const. Notice that it's a const value, so we're not going to modify anything in the array. We're just going to read the array. But we are passing the search value in here. Okay, let's do it. So I'm going to go back to searching algorithms and make a brand new function, and we're going to call this binary search. And instead of bin search, we'll call it binary. Here's my binary search function. I need two parts, an array, integer array, and a search value. So here is an integer array, integer array, that's what we're going to call it as well, and a search value. Search value is an integer single. There we go. Okay, it's going to return out an integer, and this is going to be the index, right? So whatever the index is going to be, right? That's going to be the return value. Okay, so if the index, if found, right? Now we could also return something else. Was it found or not? Instead of returning a -1, we can return, you know, if it's found, then get the index. If it's not found, we can do that too. But for now, we're going to keep it just like it was in C++. So now we have a few variables that we're going to use: lower bound, upper bound, and mid. Let's do that. So we're going to say local variable, lower bound, integer, upper bound, integer, mid, integer. Right? Those are 3 integers that we're using. Okay. So let's set those up first. So sequence, And what I want to do, let's get rid of this return node. We don't need it right now, but we will have it later on. I'll put it down here for now. So the first part of the sequence is let's do all this assigning. It can be done on one line because one thing isn't affecting the other thing. They're not related in any way, right? So lower bound is equal to 0. So we'll set that to 0, right? And then upper bound is equal to array num minus 1. So upper bound, set upper bound to array, this one, get integer array. Here it is. And we want to know the range, so it's the length, right? Array length, here it is. And then we have to be careful about this, minus 1. That is this. And this part is going to be set to the upper bound, right? And then mid is going to be just declared, so it's also 0 starting off. So again, we're just going to say that mid, we're just going to set it to 0. So we set all those things up. Okay, mid 0, lower bound 0, and that's the first sequence in my, kind of that I have here. All right, just initializing values, and we can actually make a comment here that's like saying something like initialize values, right? Initialize, or initial values is fine too, but initialize. There we go. Okay, and now the next part is a while loop. So do I have a while loop? I do, right? So while this condition is true, loop. That's how a while loop works, right? So what's the condition? The condition is where the lower bound is less than or equal to the upper bound. So lower bound is less than or equal to the upper bound. If that's true, loop. Keep looping while this is true. Well, let's take a look. Lower bound is 0. Upper bound is the integer array length minus 1, right? So it's definitely going to loop this the first time, because unless the integer array is empty, in which case it's going to not even do this part at all, right? So there's my while loop. We also have, I'm just going to skip one. I'm going to go down to this one. If the while loop fails, or if we get through it somehow, if we go through the while loop, then I definitely want to return, here's my return node, I want to return minus 1. I'm doing this because I know that here's the while loop in, in the curly braces, but then there's this return minus 1. So if I get to this return, that means I didn't find my value, right? So value not found. That's what this is. Value not found. Because we're returning minus 1. Minus 1 means that we couldn't find the value. That's why we're returning minus 1. Okay, but what about this one? This is where I find the value in here, the while loop. All right, so the first thing in the while loop, I'm going to say set mid to upper bound plus lower bound divided by 2. All right, so let's do that. So I'm going to set mid. It's my first thing I'm going to do. So I'm going to do a sequence node because I'm going to do a bunch of stuff in sequence. So upper bound, upper bound, we say, plus lower bound. Adding those together. So upper bound plus lower bound, and we want to divide that by 2. So divided by 2, right? Upper bound plus lower bound divided by 2. Now when we do this, what if there's 2 integers, what's going to happen if we just divide it by 2? Does anyone know what happens if there's 2 integers that we divide? Does it go higher or lower? What does it do? What do integers do when you get a fraction? Lower, yeah. And the reason why this happens is because, for example, if I get, it does round down. If I get 6 and 5 is 11, right? And I divide 11 by 2, I get 5.5. 0.5 is truncated. It's gone. It's even though, because an integer can't hold a decimal. right? So then that 0.5 is truncated, it's cut off, right? Which means it goes down to 5 immediately, right? So that's what this does. So then even though this is division, I'm still going to return this value. And that's what mid is. So it's going to round down. That's what this version of our code does. All right, so that's what it rounds down. It kind of creates the midpoint. And now we check. The next thing is if my array mid is equal to the value, then return mid. Value found and return the index. We want to do this because this is an early exit. Okay, so let's do that. So first thing we do is we set mid and then we check if mid, right? And mid is just the index that we're getting, because all we're looking for index. So array mid, which means the array, so that get integer array, and I want to look for a get. I want to say if this value is equal to the search value, get search value, right? If this is true, then branch. Good things are happening if this is true, right? Because if this is true, we're in luck. We found the item and we know where it is. Mid is the index that we're going to use. So we're going to return mid. So we can get that return value that we used right here. And we're going to return it right here where we return mid. Okay? That's if the value is found. That's the first case. There's also an else if. That means it's false. This is false, right? So now the next one is, what about if the value is less than the array mid, right? That's the second case. So that means that's in here. So we did an if, and when we do an if else, those three things that we're doing, if you consider what that is, if else, false is else, right? It failed the test, right? But now we got to do another if, which is this one. If value is less than array mid. So value, search value. If the search value that I'm looking for is, get this, is less than this, that's what I'm saying. If value is less than array mid, then upper bound is equal to mid minus 1. Then branch. Okay, if it's true, if this condition is true, then upper bound, we're going to set upper bound, is equal to mid minus 1. So mid minus 1. But we also have another case if this is not true. So what if, it's not less than? That means it's greater than, which means that lower bound is equal to mid plus 1. So lower bound, lower bound is equal to mid plus 1. Okay, and I'm just going to make this so it's bouncy a little bit. There we go. All right, so that is that if statement. Okay, that's what it does. So the only time it returns is if, as an example, we found it right here. So if you know, we go through, we do a while loop. The first sequence is upper bound divided by 2. We set the mid, right? And then we say, well, did we find it? We did. Return it. What's the index? If we didn't find it, then what we do is we set up a new midpoint. We set up a new upper bound and lower bound. And then once we set these upper bounds and lower bounds, when we come back to the while loop, we test the lower bound and upper bound. Again, remember, this is the test. This is our condition that continues to make us loop. That's what's happening here. Okay, so these are our variables, and that's it. That's our algorithm. Now, if you really want to put that in, right, we can do some comments, but basically, it's, you know, here would be that search value found, right? That's what that is. That's when it happens, right? When we get to this. This is where the search value found. This is where the search value is not found. So we'll say search value. And if you really want to be descriptive, we can, you know, make it red. Oh, we can make it red, I said. There we go. And if you really want to do, we can make this green, just cause. There we go. Search value found. Search value not found. Okay, so now we know that this is the way it works. This is our main loop for the algorithm. Let's test it. So now that we have that, I'm going to go into, after I've done my bubble sort, so I've done my sorting algorithm. The array is sorted, right? That's what I can do. And I'm going to pass out this sorted array into my binary search. So if I do binary search, here it is, right? This is why it's good to have this. My integer array goes in there. So instead of me having to go put this node over here again, that's why this is good, because it passes it through, right? Search value, I'm going to look for a value that does exist, right? And I want to know the variable, the index. Let's search for 11, again, the last value way over here, okay? Now remember, it's going to be sorted first, then it's going to be found, all right? So I'm going to look for 11. So that's the value that I'm going to look for. Okay, and let's see the index that I'm getting. So I want to print, and I'm going to print out this index. But what I'll do, we'll say, we'll do an append string, and we'll say that, you know, if we found the index, we'll know, but this is what it's going to be. The index is whatever. If it's -1, we know it's not found. Okay? And I don't want to make it some more complex than this. So if I press play, then it says index is 11. So to know this, if I look at my output, it says index is 11. Let's see if that makes any sense. So if I look at my grid character, I'm looking for 11 too, right? And let's take a look. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. By luck, it's 11, right? Even though we have multiple ones, right? Its index is 11. It found the index. Okay, let's look for 14. Not found. So what we're hoping is that it's going to give us index -1, right? To look how this works. So let's go back to grid character, and I'm going to search for 14, right? Compile and save. And then if I press play, it's going to say index -1. There's index -1, which means not found, right? And let's try another value, something like 13. So let's try 13 out and compile and save. We'll just do it here. And we can see that index is 12, right? Well, if index is 12, let's take a look at that and see if that's true. If I'm looking for 13 and my index is 12, right, then there it is. There's index 12, 13. The very last value is 13, right? So this would have been the worst case scenario, because it would have sorted this way, and it would have kind of split the thing, keep splitting until it found, you know, the value. So this is your binary search. Okay. Questions around this stuff? All right, so this is what I wanted to show you. We have to be able to convert as developers with Unreal Engine. I know you guys, a lot of people have said that you really like Unreal Engine. That's good, but you know, as developers with Unreal Engine, we're going to get code, C++ code or pseudocode. Someone's going to give you something and go like, I want to do this. How do I do this in a blueprint? Especially if there's an algorithm you're doing for AI. You're going to be given an algorithm for AI, and then you have to convert this into a blueprint. And it might be a very complex algorithm that you're looking for, especially when we get into the second half of semester, which is going to be for pathfinding. Or if you're going to make your own decision tree, you know, kind of thing. And, you know, the next course we're going to do, you need to follow an algorithm. There's something that's already existing, you know, as an example. You need to know how to do it. All right, so this is good. Just going to continue through here. So we've talked about the binary search. I do want to talk about, we're going to take a short break soon. I want to talk about recursion. And the recursion is a very common thing we do with algorithms and data structures. And the reason why we do recursion is because it can be a more elegant solution than using a while loop. It can be. It can also be very confusing for people when they first use you know, a recursive function. Have you guys done recursion at all? Anywhere? Like in your code? Like with Connor, perhaps? Because he's the only person that might have done it. No? No recursion? Do you know what I'm talking about? Oh, Griffin's done it before. Yay, Griffin, right? It's like where you're having a function that calls itself. So the function calls itself. So how recursion works is when the function calls itself, it makes a copy of the function that puts it on the call stack, right? And so what happens is every single time it calls itself, it makes another copy of the function and puts it on the call stack. And it keeps doing that over and over again, right? And I know it's pretty crazy. So as you keep on making a copy of the function, then what happens is when it gets to the base case, that's what happens, then it resolves, and then it returns its value to the previous function, the copy of the previous function of itself, right? It almost clones itself a bunch of times, right? And then when it goes to the base case, it returns back the value, keeps returning back to the calling value, keeps doing that, and then keeps popping stuff off the call stack, pops it all off the call stack until it's back to where this function was called, the original function, and that's how it does it. Now, if you talk to Connor or anyone who's coded before, they'll tell you the same thing, which is normally we can replace a recursive function with a while loop. Okay, it's possible. Or looping structures, regular looping structures. They just might be bigger, right? So instead of it being like really, really tiny and beautiful, because it looks like it's going to call itself, you know, as an example, it's like really, really big. I think they do because what happens is with recursive function calls, you know, most people don't know how to A, read them. They're not very readable, right? And B, they also they often cause infinite loops if you don't make the base case very understandable, you know, as an example. All right, so that's the problem with them. So let's talk about this. It's like you're looking into like a mirror. You know, you have two mirrors and they're looking at each other, right? And it's almost like this infinite mirror, right? So what we want to do is we want to call the function multiple times with values that are narrowing in on the thing that you're looking for or the thing that you want to do, right? It's kind of cutting the value down, you know, until you're getting to that base case. The base case, or the base condition, if you will, is what you need to stop this infinity, right? Because it'll keep going forever. It'll keep on calling itself until it's done, right? Or until the computer breaks because it's an infinite loop, you know, as an example. All right. So we can do both things, and I'm comparing here recursion versus iteration. So again, recursion, it terminates when the base case becomes true, whatever that condition is, the base condition. Where iteration, it terminates when the condition becomes false. So if, for example, if the while loop failed in our previous example, then we would just skip out of that whole while loop and we would go into the return node, right? You know, recursions implemented with functions, iterations implemented with loops. Okay, that's the difference. Every recursive call allocates more stack memory, and what you can have is a stack overflow. if it loops enough times, you'll get the famous or infamous Stack Overflow, where you run out of stack memory. Where every iteration does not require any more memory, right? It doesn't require more memory at all. Recursion, lots more memory, right? Recursion, smaller code size. Iteration, because you're using a loop, much bigger code size, less elegant looking, right? Recursion, less performant, because I'm instantiating a copy of my function and putting it on the call stack. I'm using memory, right? Iteration, more performant, because I'm not using any more memory, right? So one will cause a Stack Overflow, the other one might cause an endless loop, okay? So those are the negative things that can happen. So when we want to use recursion, okay, so case one, when the implementation of the recursion is much simpler, way less complex, like when your mind looks at it and goes, we just got to call this function again from within itself. If you can say that in your mind, yay, that's when you want to use it, all right? Case two, when we can be reasonably sure that the depth of the recursion will not cause a Stack Overflow. That's the second case. So if it's really simple to do, but then you're like, wait, it's gonna take a long time. It's gonna, kind of the iterations over and over again, calling itself. It's gonna cause many thousands of stack calls. I'm gonna keep on making copies of itself over and over again. Bad, right? Of course they are. RAM pricing is insane right now. So you could make it a recursive binary search algorithm, and it looks like this. So here's an example of a recursive binary search. We're not doing this, okay? But take a look at how this looks. There's no while loop, okay? So the way it is we have a few different inputs: the search value, the lower bounds, the upper bounds, okay? And then if lower is greater than upper, then return -1. Value is not found, right? So it happens right away. Otherwise, mid is upper plus lower divided by 2. We still do that, right? And then if value, the search value, is less than the array mid, then return, call binary search again, right? You're passing in the value lower and mid -1. And then else, if value is equal to the array mid, then return it, and that's when it's been found. Otherwise, return recursive binary search mid +1. So what happens is, because the values that we're getting inbound, right, are changing when we call the recursive the function itself, that's what causes the iterations. It causes that kind of the way of moving. So this is now a question for you guys is this simpler? Like if I look at this and I look at the original one, this one. Okay, to me, this is simpler in this case than the recursive binary search. This is not as simple, right? So the first case is already broken. If it's not simpler, like to look at, don't use it, because that means that it's going to be more complex for you to understand. Griffin's like, yeah, the iteration is more straightforward. Yes, it's true. It is more straightforward for me. But you're going to come to a point where you're like, wow, man, I wish I could just call this function from itself. It's going to come. You're going to, as a developer, you're going to get to that point. If I call this thing, it's a recursive function, and it's nice and easy. And then you're going to run into some problems. Okay, so let's go to the next one. A linear search, jump search, right? Faster than a linear search, but not as fast as binary search. Works by jumping ahead by square root n steps, and then performing a linear search. So it's actually a weird way of doing things where this does not require a sorted list at all. So this is another one. So again, here's something to try. If you want a challenge, implement the jump search and see how this works. Okay, and now we're just talking about performance. Okay. Interpolation search. Here's another one if you want to try this one. So there's a couple of challenges here that you can try on your stuff. So a modified version of the binary search that tries to estimate where the value is, and it works well if values are evenly spaced, right? It doesn't work well if they're clumped together. All right. So this is where it can actually be this is a performance bump. We're looking for improving performance on these searches. Imagine now we only have a very small list of 11 values or 12 values or whatever it's going to be. But what if we had 12,000 values, right? So when we're searching for a value that's within those 12,000 set of values, now we need performance. Every little bit counts. All right. So doing things like low and high, and in a while loop, that might make sense. And again, it's the exact same thing as a binary search, but it's an interpolation search. Here's another one, exponential search. So quickly finds a range using powers of 2 and then applies binary search. So it's useful when the size of the array is unknown. You don't know how large the array is. Somehow you can't find that size. And it could be because, the size is changing. Let's suppose the size is constantly moving. Let's say you have a bullet pool or something like that, and the bullet pool continues to get larger or smaller somehow, which is dangerous, by the way, if you ever did something like that. Then you could use some kind of, here's the binary search, and then you can use an exponential search that uses the binary search to do the thing that it needs to do. All right, so that is powers of 2, an exponential search. And the last thing we're going to talk about is something called hashing. And hashing, basically what it does is it stores and retrieves data very efficiently. It's widely used in databases and cryptography, data structures like hash tables, as well as checksum validation and password storage. All right, so that's what it does. And what it does is it converts an input key into a fixed size value, which is the hash code, and it uses that, uses a hash function to do that. So a hash table, what is it? Why do we want to use it? Hash table is a data structure. So algorithm, data structure. Data structure would be a collection, in this case, a hash table. It's also called a hash map, right? And it basically stores key value pairs, like a dictionary. So for example, I might have a name, a string, and it returns a value. For example, I want to know player health. Player health would be the value, the key, or the thing that we're looking for. And the value would be something stored inside of that dictionary. So we can have an array of data inside of a hash map, a hash table, where we have string names of things that we want to access. Health, strength, intelligence, whatever you want, all your player stats. And then you put that inside of in key value pairs. And then when I'm looking for something, instead of me looking for an index like index 0, 1, 2, 3, I'm actually searching for, I'm using that the key. I'm looking through the hash table with a key, and it's giving me that value back if the key exists. If the key doesn't exist, it's going to return -1. Okay. So why is it really cool? It's used in fast lookups. It's constant time on average, which is amazing. It's not linear, but it's pretty good. So O of 1. Sorry, it's the other way around. It's really good. It's better than linear. It's not an O of n. It's O of 1. So it's as good as looking up an array value. Like I want to look at index 0. That's O of 1 from a complexity perspective. And then it's really efficient in insertion and deletion, but it avoids duplicate elements, and it stores a huge amount of data in terms of how it works. So hash tables are something that are built into most, kind of like languages. And what I wanted to show you was that, here we go. Here is Unreal Engine, and you can see that Unreal Engine has the following data structures that are built into it. And these are the only ones it has, by the way. Okay, so here are the containers: T-array, like we talked about before, a T-map, which is a type of hash table or dictionary. If I look at that, then what T-map will show you is how you can use it. Okay, so a map. And what it does is it uses the heap instead of the stack. So it uses your big memory. So here's an example of what I talked about before, where we have a value, as an example, or a key, and then a value at the end, right? So that's how it works. We use the add key, the add function to do it, right? And that's how it would work. That's in C++. And let's see if they have it in. Probably don't have it here in. But what we can do is I can show it to you here inside of Unreal Engine. Here we go. So if I wanted to use a map, it's very simple actually. So here I've got my grid character, and if I want to develop, create a map of, key value pairs, so I can just add a new variable. We'll call this, I don't know, attribute map. Attributes. Let's call it attributes. And instead of it being a Boolean, you can choose whatever you like. So let's say if I go to string, right, as an example, then on the right I can choose a map. And notice it says string, and the next part is an integer. Take a look. So it's a map type. The instead of it being an array, I can use a map. So a map basically gives us two values, string and integer, right? Where the string is the fancy name, the name that you want to use, and the integer is the value. So key value pairs. That's how it would store inside of this. So how I would use it is if I go to set attributes, right? Here's my set attributes for my my value. Actually, I would actually just do a getter. That's the way I would do it. Here's get attributes. And then from there, if I want to do an add, I want to add an attribute. Here's my attribute. So here's my key, and this is my value. So for example, my key would be something like health, right? And let's say my health is 100, right? And then I can add another value. I can say, well, I also want to add another one. So I can, let's say something like add, and let's say we would do this as an example in sequence, or you could do it in a loop. And let's say I wanted to do something like strength. Maybe my strength is 40, whatever that means, right? And then, so that's how you would add values to the map. And then when retrieving values, it would look like this. So I would get, sorry, I want to, so the things that it has with it, so here's map values. I can clear or remove, right? I can remove a value. So there's the value that I can remove, right? And I can select a value, right? So I can select values. So here's option 1 or option 2. Really good ways of doing things. But that's kind of what it does. And if you look here, if I go back to my map, right? So this is my example of my fruit map where I have keys. They use the integer keys, and values are strings in this case. So it'd be the other way around, right? So look, it says where it says find or add. So if I do a find, you can see that is a thing that I can do. I want to find this. Do I found it? Can I find it? And this is kind of the way I can do it. If I want to find health, then it would give me the Boolean, and here the value that I'm looking for. So I'm looking for a key, and I'm getting a value, which is pretty cool. So that's another way of using things. Instead of making it a sequential container like a list or an array, you can use something like a map. Okay, I know that it's not as intuitive for a lot of us to do this, but it's actually really effective, especially if you don't want to create a struct, as an example. I don't want to make a struct. I want to look it up, and I also can check to see if it exists. If it doesn't exist, it's going to return nothing. Like for example, the way it works is if this key doesn't exist, then it will return false, right? Okay, so I can search for stuff that's in there, and it'll return false. If it does exist, it'll return true and the value. Okay, that's important. So what about replacing a value? So if I want to change my value of health, I just add it again. So what it does is if it found the key already, it'll just replace the value if it finds the key, if you do another add, right? Whereas if the key never existed, it'll add a new one, okay? So what else can you do? Can you iterate over this thing, right? Because you want to be able sometimes to iterate over a map. So could I do a loop of some kind, right? Like, can I do a for loop? Can I do a while loop? Can I do that kind of stuff, right? Can I, what other operators can I use? If I look at utilities, these are all the things that you can do. Is empty. Here are the keys. I can kind of outputs an array of all the keys that are present. So that is very helpful. I can also outputs an array of all the values that are present, if that makes any sense, right? So which is pretty cool. These are really helpful. Okay. I can also remove a key or delete it if I don't want it. I can find the length of this thing just like an array. This is very useful stuff, and I can also check to see if something is contained, whether a key is in the provided map or not, which is pretty cool. So this is really great stuff, guys, and it gives you another tool that you can use in your toolbox when it comes to storing and retrieving values, other than using a list or an array, okay, or a struct. Questions around maps? All right, so that is maps. We talked about those things. And I'm just going to go back to those data structures. So maps and sets. Okay, so this is the last one that I want to talk about and before we take a break. So what is it? What it does is it gives you a set of objects, right? There is no key value pair. What it does is it kind of, for example, it only allows you to have, if I'm not wrong, a unique value, one unique value in a set. So, so you can keep on adding as many values as you want, but it's going to be a unique set of objects that are in there. Like it won't allow you to add in the same thing over and over again. All right. So you can change a value, right? So using the in place method, and you can add stuff as well as you can do removing and a bunch of other things like that. So you can go through the fruit set in this case and look through how it works. So how does it work here? So remember that we said that this was a map, right, for attributes. So that's one option. And notice we can also make it a set. So those are all the different types: array, set, and map. So let's add a set. Let's call this, we'll call this equipment. And it will be a string set. So I'm going to go back and just make it a set like this. Here's an equipment. And notice you can decide what type of set, like what is your data that's in there, as an example, right? So if I go in and type in equipment, there it is. And then again, you can look through set functions, and these are all the different things you can add in. So you can add, right, an item to the set. You can add items, multiple items. So you can get an array of items and transfer them over to the set. You can compare if one set intersects, if there's elements in one set that intersect with another one. So example would be, I have a bunch of numbers, 1, 2, 3, 4, 5 in one set. And then I have another one that is, 5, 6, 7, 8, 9 in the second set. And because 5 exists in both sets, when we use the intersection, it returns the value that exists in both sets. 5, right? So that's how it works. Union, what it does is it returns both sets together. So it takes one set and the other set, combines them, and makes one big set, right, of numbers. Again, the reason why we'd want to use these things is if I wanted to have unique values, as an example, and I want to be able to ensure, like from a data integrity perspective, that I have a set of these values and a set of those values, and then I can make comparisons between, two data sets, as an example. Okay, sets are really great from if I want to do an analysis, anything like that. Remember, Unreal Engine can be used for all kinds of stuff, not just games, right? So this might be something where it might be helpful for us to use. Personally, I haven't had a lot of call to use sets. I've used maps before, but sets in my coding career, not a lot of use. And you may not have a lot of use either, but it's there just in case you need to solve problems. Okay? So those are the type of things that we want to talk about today from a data structures and algorithms perspective. I'm going to put this up, so save, and then on the break. But for now, what I want to do is, because we've kind of reached the end of of where I want to go. The next part that we're going to get to is what you need for your assignment 1. Okay, so I wanted to talk about this. And by the way, the discussions we're having about data structures and algorithms are the things you need for next half of semester, as well as when we hit this again in AI2, right? Because in AI2, when we're creating a tree structure, how do you know what a tree structure is unless you actually like can put things together yourself? You need to be able to do things on your own sometimes, my friends, and you can't do that unless you know what those underlying structures are. Okay, so we're taking a short break, and when we come back, we'll get into assignment. We'll finish off obstacle avoidance for assignment 1B.